Good day, judges. I am BANDARU YASHWANTH, and today I'll be presenting my team's project, the development of a ventilation energy recovery appliance for InTalk Global. Along with me is my teammate KINNON, and we are representing the School of Science and Technology, Singapore. Today, I will be talking about the problem of sustainability. Firstly, we were asking ourselves, why is clean energy important? Clean energy is important, and it is extremely useful to us because it does not harm the environment, it has lower setup costs, world is running low on fossil fuels, and it benefits the earth in the long run. The problem we were asking ourselves now were how can we harness wind energy of a ventilation system in buildings? There are a multitude of reasons as to why the team had sought an alternative to traditional wind turbines. For one, traditional wind turbines need large amounts of clear windy land. Another reason is that the costs of upkeep and construction are high. Lastly, wind turbines have the tendency to kill birds and disrupt the local ecosystem. In our local context, it is a well-known fact that land is a limited resource for us. However, what is not lacking in prevalence are ventilation systems that are practically found in every building. Next, I will be talking about our solution. The team aims to utilize wind cowls to generate electrical energy. When the wind hits the blades of the cowl, kinetic energy is transferred from the wind to the cowl. The cowl would spin and ventilate the building. Hence, what our team plans to do is to harness the kinetic energy from the cowl. This is a schematic of our team's solution. So, how does our solution pertain to STEM? In the area of science, the fundamental principle behind our solution would be electromagnetism. As the electrons in the copper coils of a generator move when they are exposed to changing magnetic fields, which is a result of magnetics in the generator spinning, an electrical current is induced. In the technological aspect, the generators generate and store electricity, which would be subsequently supplied to the electrical appliances. Moving on to the engineering aspect, our setup attempts to mimic an environment reminiscent of a home to simulate a scaled down version of what our solution could be. In this regard, the team has also had to determine the optimal placement for the generators to minimize energy loss. We had to consider factors such as the tension of the belt, distance from the cowl, and the number of generators that we could practically put. Finally, in the mathematics aspect, we used Ohm's law as well as data from multimeters and fixed resistors to calculate the appropriate current output. Overall, the use of STEM has allowed us to come up with a more efficient design for energy generation. I will now be talking about our solution's applications. Due to the solution's simplicity and scale, the team had to overcome the traditional pain points associated with setting up wind turbines, which include the environmental impacts, the high financial costs, and the large swaths of land required. Our solution would be able to operate in an urban setting, a market that has substantial areas for development. This is a side-by-side between the schematic diagrams and the actual solution. I will now talk about our solution's effectiveness. The relationship deduced from this voltage to rounds per minute graph is that these two factors are directly proportional. The correlation for the voltage is the RPM multiplied by 0.039. Moving on, the relationship deduced from this voltage to wind speed graph is that the voltage produced increases as the wind speed increases. However, the voltage starts to level off when wind speeds start to exceed 30 meters per second. Hence, the team has concluded that in order to generate a stable voltage of 8 volts, the wind speed needs to be held at around 25 meters per second. We will now be showing you a demonstration of how our prototype works. Now that you have taken a look at our prototype, I will be talking about our solution's improvements. Currently, the team uses a 3-phase AC generator in a delta network configuration. The alternating current causes the light in the setup to flicker. Therefore, the team planned to change the same configuration into an AC star configuration instead. This would allow us to rectify the output into a DC waveform, resolving the problem of the lights flickering. In summary, our solution's simplicity and potential scalability makes it applicable in many areas, especially urban regions. While the team acknowledges the areas for improvement, we believe that we are taking the first step in the right direction towards developing an alternative sustainable energy source. Thank you for listening.